Okay, good evening. I'm Dave, KE4EA, joining you again. You've been seeing me the second half of the first three lessons that we presented, Chapter 1, 2, and 3, and so I'll have the entire evening tonight on Chapter 4, and also next week as we do Part 2 of Chapter 4. Now, anybody that might be joining us in the future, I highly recommend that you go back to the first three sessions of this series and pick up the introductory material that I present in the second half of weeks 1, 2, and 3. That way you won't be lost when we get into Chapter 4. So just by raising of hands, just for my curiosity, that's optional, but how many people are viewing the Kessler videos? You just wave at me if you are. Okay, good. Yeah, probably half or more. I hope those are helpful. He gets a little heavy sometimes, but as we've said in the past, when you get things from multiple points of view, sometimes things connect that wouldn't otherwise. And just let the stuff that goes over your head, let it go over your head. It's all right. We're going to cover what you need in the class. You might want to have your extra class reference sheet handy tonight. We'll be making some references to it. I've got pictures on the slides, but if you want to take any notes there, you could. And most of you figured this out already, but we don't necessarily follow the order of the book. We had a student one time that complained that he wanted to take notes in the book as we were going through the material. Well, we don't follow the book very closely in terms of the order that we present. So just if there's anybody that was confused about that, I wanted to share it. Very good. And in the past, we've usually recommended, or at least offered to people, to maybe look at the last time we presented a class before seeing the current one. I haven't been doing that in this series because so much of the material has changed, especially in Chapter 4. The basics are still the same, the core material, but there's an awful lot that's changed. So if you were going back to Gary's website or his YouTube channel and looking at that, you'll see some things that are different tonight than what we've talked about before. All right, with that, we'll move on to something we shared last week, learning strategies that work. I think most of you have seen this or looked at it if you weren't with us in the class, and just wanted to remind you that the strategies that work, I've circled there in blue. Spaced repetition using the AppSpot tool, the ARRL exam review site, going chapter by chapter every few days. Spaced repetition, so go back to Chapter 2 and Chapter 3, and of course Chapter 4, only half of the questions we'll be covering tonight there. So, but it's not a bad thing to look at questions that you haven't covered yet, because it'll plant a seed in your mind saying, hey, I want to learn about that, and that'll be coming up next week, the part that isn't covered tonight. Self-testing, and then permanent learning takes time, as we saw. Sleep on it, spaced repetition. We don't want to have this be the result of your efforts. Solid brick wall of learning. Okay, so with that, we'll move into Chapter 4, Radio Mathematics. And we'll cover a little bit less than half of the pool questions tonight, but we'll be covering most of the harder ones. Next week, a number of the pool questions are easier, so it'll be fine that we do a few more. Okay. So I found this image on the internet someplace, which I thought was quite appropriate. We can't really see what's happening with a lot of the math that we're dealing with, and that's why we need to use equations and math to get a good understanding of what's really going on. Graphs are really pictures of equations or formulas. And in a bit, we're going to see that there's two types of graphs that will show the same information in different ways when we get into rectangular and polar discussion. This was a new pool question in the current question pool where they ask about linear versus logarithmic scales. And the point that they were making was that with logarithmic scales, you can get a much larger range of values. So here's an example of a logarithmic scale, and notice how it's going up by tens, 10, 100, 1,000, 10,000. To get data in that range onto a linear graph, see, it'd be very hard. The top of that one is 4,500. Even if you space these out, it would be much more difficult. So the point that they're making and what will appear on the pool is why do we use logarithmic scales for this scale when we're talking about frequency response. Another thing that you'll see commonly, especially in the ham world, this will often be a logarithmic scale over here, going up by decibels. Which I mentioned. They'll either increment in powers of 10 or go up by decibels or something similar to that. And as we have, Gary explained to us, blue text is significant. That means you're going to see a pool question in that area. In this case, I normally will go through some background on what we're covering and then restate some of that in terms of the way it appears in the pool. So the y-axis, which is the vertical axis, often uses logarithmic scale for graphs of circuit frequency response or large ranges of values. It's easier to graph. All right, well, let's go hiking. Yeah, we're jumping around here a little bit. So here's a guy with hiking poles. We've got a map and a compass and a step counter here. And first thing we're going to look at is the concept of rectangular coordinates. And I'm going to say that there's two ways to get to a destination. The first way is shown here, where I tell you, you go 400 steps this way, and then 300 steps this way, and you'll wind up at point P. You happen to be this distance away from the origin, where the x and y axes cross, x and y, that's called the origin. So I can tell you to go 400 and then 300, and you'll wind up here. This is the other one. This is the concept of polar coordinates. In this case, I'm going to tell you to strike a bearing of 37 degrees from the horizontal, whatever that turns out to be, and then walk 500 steps. And you'll notice that you will be at exactly the same point as if you would have been following the directions over here. So this is the rectangular concept, an x and a y. This is the polar, an angle or a bearing and a distance. This is also called a magnitude. So that was fun. We started out by going hiking. You've probably seen this before in 8th grade or high school math, something called Cartesian coordinates, XY scale. Two axes, horizontal, which is x, and vertical, which is y. Again, where they cross is called the origin. And a data point is identified as an xy pair. So this is 3, 4. Means 3 over x, 1, 2, 3, 4 up. So that's how you find a point. So this is just in simple rectangular coordinates. We're going to be talking in terms of complex numbers, where we're going to be plotting resistance on this scale and reactance on this scale, or real numbers and imaginary numbers as we work our way through all of this. So how are we going to remember x and y? Because the x and y, in terms of the axes of the graph, show up in several places in the pool questions. And I've got a little trick that, well, I know what it is now, but when I was getting confused about this, that this was helpful to me. Think that x, the letter x, has 2 feet. So it's able to stand on the line. So this is the x-axis. Now y would tip over. Okay, so the bottom of y is really a fence post, and it holds the letter upright. You can kind of see the fence post aligns with the y-axis. So if this is new to you at all, what I'd recommend is first of all, remember that x stands on the x-axis and y is the fence post going in the direction of the y-axis. Close your eyes and visualize, see if you can see the x and its 2 feet, the y and its fence post, And then open your eyes, look back at this, and presto changeo, it's still there. We just did some recall practice there. Now, this next slide has got a bunch of, this is background in context. So just kind of hang in there with us. There aren't any pool questions on this slide. But real numbers are familiar to us. Real numbers are like counting numbers, 1, 2, 3, 4, 5, pi, those sorts of things. And here's a crazy, crazy concept. Kessler got into this a little bit. The square root of -1 is defined as an imaginary number. And it's easy to see why you would consider it imaginary, because no number times itself can ever be negative, right? So this is something very special. And why is it even necessary? Why do we even want to consider this foolishness? Well, it's necessary because real numbers don't adequately describe everything in nature. So you'll see imaginary numbers in physics and electronics all over the place. So that's why we need at least a little inkling of what's going on. And mathematicians use the letter I, and you might remember on our calculator we had that triple tap key. It was pi, E, and I. So mathematicians use the letter I. Electrical engineers use J, because I is used to indicate current. So you're going to see throughout our slides tonight, it'll be something like 3 plus J4, for example. Well, that would be I4 on the calculator to describe what we're going to call a complex number. Complex numbers are considered, they have real parts. Those are along the x-axis, and an imaginary part, which is along the y-axis. And the imaginary part is what we're going to use for reactance. Now, reactance is not imaginary, it's real, but in terms of this number system, that's what it's called. In complex numbers, do a really good job of helping us with complex impedance in electronics. They appear in other places too. We've got the I and Q signals in SDR receivers, shows up in several other places as well. So we're going to have resistance, which is the real part, combined with reactance, which is the imaginary part. I'm going to be coming at this from multiple directions because there's several pool questions that keep asking us questions in different ways. Plus, I kind of want you to get this. Some people said that, in fact, quite a few people said they'd like to get 100% on their extra exam. So I'm going to do my very best to make it possible with suggestions and repetition, memory tricks, analogies. I'm going to try to help get you there. So complex number notation in a rectangular form, by now you've got a good idea of what rectangular means, is always in this order. You'll have a number, it's real, the real part, plus or minus the imaginary part. And in our case tonight, it's going to be resistance plus reactance. The imaginary part, normally signified with a J in our presentation, but on the calculator we're going to use I. And then an actual application, a 10 ohm resistor and 25 ohms of inductive reactance may be written as a complex number. In that case, it would be 10 plus J25, or I25 on the calculator. Capacitive reactance is going to be negative. So the same thing there would be 10 minus J25. You might remember on the extra class reference sheet, we tied the concept of inductive reactance to something positive and capacitive reactance to something negative. We're going to see that over and over again tonight. Speaking of which, here we are. We're going to be talking about time constants coming up. Notice that a time constant, this is approximately 2/3 and 1/3. That might help you identify these numbers when we get that far. And here we're showing the reactance formulas. This is capacitive reactance, X sub C, and negative. I like to think of the line in the middle of the formula as being a big negative sign. So if you're if you're looking for a mental crutch to remember which is negative and which is positive, think of this formula. I'm going to have a handout that I include before next class where we're going to have maybe half a dozen formulas. I don't think it's any more than that. And I'm going to challenge everybody to fill out this table. It's going to have xc on it, x sub c, and then your job is to write the formula next to it, 1 over 2 pi frequency c. And you'll take everything that's on that sheet, be about half a dozen formulas, and see if you can duplicate that, memorize those formulas, and do it within 30 seconds. So that'll be my challenge for next week. These aren't very hard. 1 over 2 pi frequency C, or inductive reactance 2 pi frequency L. Not hard, just prepping you for what's to come. All right, I'm going to continue on the discussion. Complex coordinates, rectangular form. So we've got the x-axis, which is real, the j-axis, which is imaginary. We're going to plot resistance on the real axis. We're going to plot reactance on the y-axis, real and imaginary, plus j minus j. Again, here's an example of how it would be written. Another thing I'd like you to note here, is it possible to have negative resistance? And the answer to that is no. So when we're plotting points here, and this will be important a little bit later, you will never ever have anything in this quadrant or this quadrant. It's always going to be in these two quadrants that the values would be plotted. So what would happen, do you suppose, if a number was plotted right on the x-axis, let's say 2, 0. In that case, there would be no reactance. So if you plotted a point, it wound up right on the x-axis, that would be a pure resistor. Likewise, if there was a point that was plotted directly on the y-axis, it would be all reactance and no resistance. That would be a pure inductance or a pure capacitance. Again, this is just to try to connect some of these concepts. All night long now, we're going to be, when we talk about inductors and capacitors, we're going to be considering them as being ideal components. Most of you know that there's some resistance in wire leads, there's some inductance in wire leads, but we're...
Did you go, Val?
Was there a question there? Did somebody unmute by accident? Okay. We might need to do a mute all again there, Gary. So at any rate, any coils and capacitors, inductors and capacitors that we talk about are going to be considered ideal. No stray capacitance or stray inductance. As I mentioned, a point graphed directly on the x-axis represents a pure resistance. There's a pool question there. The same concept here on the y-axis, but there is not a pool question for that one, but you still want to know it. A point graphed directly on the y-axis, pure capacitance or inductive reactance. Again, capacitive reactance will be shown with a negative value, like minus jx or 3 minus jx, something like that. They do ask us about this, 50 minus J25, what does that represent? 50 ohms resistance in series with 25 ohms capacitive reactance. Just about all of chapter 4, you can obviously combine components in series or parallel, but virtually all of the examples and test questions are considering the series case. Okay, so that's what this means when you see it. Rectangular coordinates are used to display the resistive, inductive, and or capacitive reactance components of impedance. Putting it in the context of a pool question. That could be done in polar coordinates as well, but this is the only one that they have a pool question on. Now, we've spent some time talking about rectangular. Let's talk about polar. I like to think of polar as looking down on a map of the world, because we've got this, we've got the point in the middle, the origin, and then we've got all of these angles going out. Okay, angles are always associated with polar coordinates. So I think of Earth and the North Pole, and this reminds me of what the polar coordinate system is going to look like. And here's a picture. So we can, remember when we went hiking, we could get to a point, a destination, two different ways. Well, let's talk about some polar concepts now in terms of our class. So complex number may be represented in polar or rectangular form. And here's some maybe new term. We're always going to have a magnitude and a phase angle. The magnitude is the length of the line. Our final destination, let's say. This is the magnitude, and of course the angle is here. These are referred to as phase angles. We'll probably get into that a bit more too. This is also called a vector or phasor. So these are all equivalent terms, and they're kind of sprinkled all over the place. So when you see them, just be aware that we're talking the same thing. So this is a vector or a phasor. In a diagram like this, that's showing a number of vectors on it, is called a phasor diagram. So these things are all related. They're all somewhat equivalent. Now, an engineering purist might differ with us there, but for the purpose of our class, we're going to consider them the same. So we saw the hiking analogy. Oh, I just heard some thunder. I hope we don't lose our power.
Can't happen.
Can't happen, good. So anytime you see a pool question that has anything in it that's an angle, that's a clue that we're talking in polar coordinates, or the polar coordinate system. So that'll help you with a couple of the questions. Complex impedance in polar form. Remember in rectangular we had something like 3 plus J7, for example. So now we're going to spend a little bit more time talking about complex impedance in the polar world. So as I said, if an exam question mentions a phase angle in relation to impedance, they're talking about polar form. And this will help you with a couple of questions. Impedance is described by phase angle and magnitude. You saw that. Here I'm restating some of what we've talked about in the context of the pool language. In inductive reactance, we'll have a positive phase angle. With rectangular, it was positive J number. Capacitive reactance will have a negative phase angle. A phasor diagram is used to show the phase relationship between impedances at a given frequency. You know, I don't remember if it was the book or Kastler made a real big deal that anything on the phasor diagram all has to reference the same frequency. Again, restating this. A vector or phasor is a quantity with both magnitude and an angular component. Magnitude and direction. All right. Now there are some classes of calculations we'll need to do where it's necessary to convert from rectangular form to polar form. And our calculator is really going to be our friend here. So we're showing a triangle here. And in your good old days in 8th grade or high school math, we had our angle here. This is a right angle on this side. We had an adjacent, an opposite, and a hypotenuse, just to connect you with some of the language you might have heard before, none of which we're going to need. Or in Kastler's case, he used rise and run. But that all refers to trigonometry, which we're going to spare you from. Page 4-3 in our license manual is a whole page of how to do that with trig. If you're interested in that, look at it. Otherwise, feel free to skip it. Some calculators will do rectangular to polar, and the other way, it's built into the calculator. And ours has a feature that will do that. Our calculator is our friend. Now what I'm going to do is step over to the calculator cam and have you follow along with me if you would. So here we are. Turn on my calculator. Always press clear to begin. And we're going to put in the number 3 plus J4. 3 ohms of resistance, 4 ohms of inductive reactance because it's positive. And then we're going to see what happens when we press enter. So I'm going to do 3 plus, now to get to I have to tap this key 3 times. That's I, and then E, or excuse me, pi, and then E, and then I. 1, 2, 3. So it's 3 plus I, J, 4. Now something very magical is going to happen when I press enter. So this is in rectangular form. I'm going to press enter, and it's going to display in polar. So we're going to wind up with a magnitude of 5 and an angle or a phase angle of 53. So what you have just done, if you followed me with this, you've just done your first rectangular to polar conversion, and you used no trig. So you can say thank you now if you want.
Thank you, Dave.
You're welcome. I'll turn myself off there. And I hope you'll agree that that wasn't too hard. That was really easy. So when we can get a problem set up and put it in rectangular form, we'll get the magnitude and the phase angle just by pressing enter. And you might remember when we set the modes in the calculator, we set a display mode that would show us polar. And that's how we got there. So if your calculator didn't do that, you might not have the mode set correctly. And we covered that in a previous video, and it's also in the reference sheet tutorial document on the first page. Now, resistance versus reactance. I've copied some material over that we introduced in the general class license that I thought was very valuable. Resistance is the opposition to the passage of DC, we understand, or AC current. Okay. Reactance is the opposition. Things get weird when we get into AC. Reactance is the opposition to the AC current flow through an inductance or capacitance. So AC in inductors and capacitors do some freaky things. Inductive and capacitive reactance. And I put this chart together. So we've got the type of resistance to AC flow. We've got pure resistance, R, measured in ohms. Does it change value with frequency? No, it does not. It's the same as DC resistance. And then we have reactance. This is the opposition to the flow of AC current due to capacitive or inductive reactance. And that's symbolized by X sub C, reactance capacitive, or X sub L. It's also measured in ohms. It does vary with frequency. You might remember the formula that we showed or reference it on the extra class reference sheet. The formulas are both contain 2 pi frequency L or 2 pi frequency C someplace. So the value of reactance changes with frequency, and it's unique to AC. And then impedance, taking it to one more level, the combination of resistance and reactance, symbolized with a Z. It's also measured in ohms, ohms AC. It varies with frequency because it has some reactance value in it, unique to AC. So I thought this table kind of helped tie it together a little bit for me. So during the general class presentation or exam, there are no calculations. We're going to extend that concept now as we're going into the extra. And here we have the actual formulas. So inductive reactance, a couple of things to notice right away. This is a direct relationship, which says that inductive reactance is going to increase with increasing frequency. So if we increase something on this side, it's going to increase on this side. The indirect relationship is just the opposite. If we increase the frequency, we're going to decrease the capacitive reactance. And these are just the labels for what the symbols mean. So I wanted you to catch two things. These both vary with frequency, and they vary in an opposite manner. And I've got a diagram here that has reactance curves plotted. This turns out to be an audio frequency case. We're going to be down in the 10 to 200 hertz range. But here we've got capacitive reactance in blue. So as the frequency is increasing, capacitive reactance is decreasing. The opposite for inductive reactance. So we've got a blue curve and a red curve. And at some very magical point, they intersect. We're going to be talking about resonant frequency problems next week, but at the point on the graph where these two intersect, that's called resonant frequency. So in this case, we're going to have resonance at 50 hertz. A lot of special things about that. So just giving you some high-level concepts. We're going to put more meat on the bones as we go. Now, I'd like to take just a second and tell you where the 3-second rule came from. Gary introduced that to us, I think, last week. This is kind of a kid thing, if you want to call it that, but some kids have said that, well, if I drop my hot dog on the floor and I pick it up within 3 seconds, it's still okay to eat. Okay, well, believe that or not, in the case of Gary or myself, we both have dogs. So 3 seconds is about the amount of time that you have before the dog is going to snatch it up. I've got a little 8-pound Havanese, and I can't believe, Shelby is her name, I can't believe how fast she wolfed down a whole hot dog. Amazing. So why do we want to use the 3-second rule when we're answering pool questions? Well, we've got people that are listening to the YouTube videos asynchronously. It might be 2 months, 3 months down the road, or it might be during the day if they're working at the time that we're presenting the class. And what they like to do, when we state the question, they like to pause the video so that they can consider the answer before they have to commit to it. So if we'll give them 3 seconds, that'll give them that window. Plus, it's a lot less chaotic here in the Zoom class as well. So that's why we came up with a 3-second rule. So count to 3, 1,000, 2,000, 3,000, or whatever. So, first exam question. What type of y-axis scale is most often used for graphs of circuit frequency response? So anybody? Yeah, that was a 10-second rule, but that's okay. That's all right. It's logarithmic. Which of the following represents pure capacitive reactance of 100 ohms in rectangular notation? Capacitive reactance.
Alpha.
Alpha, 0 minus J 100. Yep, negative because it's capacitive. And it's pure capacitance, so there's no resistive component. And this series of pool questions, when they changed it, they gave you every possible combination. So you have to kind of understand what we're talking about to get that one right. How are impedances described in polar coordinates? Charlie. By magnitude and phase angle. You folks are doing great. Fabulous. Which of the following represents a pure inductive reactance in polar coordinates?
C.
It is C. It's pure inductive reactance. There's no resistance, so it's going to be right on the y-axis. That would be an angle of 90 degrees, straight up. Good, great. What kind of diagram is used to show the phase relationship between impedances at a given frequency?
C.
Charlie. Yeah, that's the only one that makes sense, the only one that we talked about. What does the impedance 50 minus J25 represent?
Bravo.
It is. Well,
Bravo.
it is a Bravo. It's 50 ohms of resistance, okay? And minus J25, the minus means it's going to be capacitive.
Capacitance.
Yep, so it's going to be minus 25 capacitive. Yep, good. This might seem kind of redundant, but this is all going to start connecting when we get into some real-world problems. Where is the impedance of a pure resistance plotted on rectangular coordinates?
X-axis.
On
The,
the,
Yeah, well, x-axis was
Yeah.
correct, but in terms of the answers that are given, the
Yeah.
horizontal
Yeah.
axis is the x-axis. Okay, good. Yeah, that's great, because it's a pure resistance. There's no reactance, so it's going to be right on the line. Yeah, you're getting the concepts, and that's what the pool questions are designed to do, to see if you understand the concepts. What coordinate system is often used to display the phase angle? Okay, that should give you a clue of a circuit containing resistance, inductive, and/or capacitive reactance.
the,
Be
the
polar.
delta.
Yep. Anytime we've got an angle involved, it's going to be polar. When using rectangular coordinates to graph the impedance of a circuit, what do the axes represent? Here you have to know x and y.
The,
I like
Well, the correct answer is
alpha.
the correct answer is alpha. The x-axis represents the resistive component. That's the vertical axis, and the y-axis represents the reactive component.
That's the vertical axis.
Yeah,
X is horizontal.
yeah. X is horizontal, Y is vertical. Another way to think of it. Yeah, absolutely. Okay, so we got through that, and that's going to be wonderful foundational information for what is to come. Just a little sidebar here on electrical and magnetic fields, but it works right into some other stuff that's following. So here we've got an example of a capacitor and an inductor, or a coil and a capacitor. So capacitors store energy in an electrostatic field. Inductors, or coils, store energy in a magnetic field. In both cases, the stored energy is potential energy. So the way these components are going to work, they're going to store some energy, and then they're going to give it back at a later time when needed. Or if you apply an AC signal to the component, it'll be storing the energy and then giving back the energy that are a different part of the waveform. So as I said before, things are going to get really freaky when we start talking about AC. But the concept of storing energy and giving it back is going to be very, very central, both this week and next week. Now, another fact here, the fields charging and discharging don't generate any heat. With a resistor, when you put a voltage across a resistor, it'll get warm. It'll dissipate energy as heat. That will not happen with inductance and capacitance with AC. I'm going to be talking more about why that happens. And just as a spoiler alert, it's because the voltage and current are not in phase. That's what causes them not to dissipate energy, but to store it and give it back. So another thing we can say is that a capacitor is a voltage device. So if we put a voltage across the capacitor and then take the voltage away, the voltage will tend to stay there until it's discharged, either by loss in the capacitor or external circuit. With a coil, when we put current through the coil or an inductor can be considered a current device. When we pass current through the coil, a magnetic field rises around the inductor until the current goes away. Voltage device, current device. A bit more on energy storage. Capacitor again, electrostatic field. And you can measure the voltage across 2 points. Again, they store and release electrical energy, as do inductors. Capacitors will resist a change in voltage. Okay, remember we said it was a voltage device? An inductor will resist a change in current. with a magnetic field that's created by moving electrical charges or current through the device. Some foundational information. It's going to be important. Now the amount, if you put more current through the coil, pass more current through it, you'll have a larger electromagnetic field that shows up around it. That field will actually be circular around the coil. There used to be some pool questions on that, but there aren't anymore. But it's just helpful to know that that's where it's storing the energy. It's storing it in this magnetic field, which actually shows up as magnetic lines of force that are circular around the coil. And the strength of that field is determined by the amount of current flowing through it. Now the voltage applied across a capacitor determines the strength of the electrical field between the plates. When you put a voltage on a capacitor, it'll look like current is flowing at first, but it doesn't actually flow. It's just piling up electrons on one side. And it's that action of piling up those electrons that makes it appear like it is drawing current. Of course, if it was a battery, it would just charge up and then the current would stop flowing. And something very interesting about coil, when you stop the current, the field collapses instantaneously. And that can cause some very interesting effects. So I'll tell you a story. When I was a kid, junior high school or so, I was interested in electronics, and there was an appliance store near our home. I could ride my bike there and drag a wagon, and they would take their old TVs and throw them out in the back field. Well, I was kind of interested in those old TVs because I could grab them and scavenge parts from them. They'd break the picture tube seal, so they weren't dangerous that way. And they wouldn't let me do that unless my mom signed a release that said I could be out on their lot picking up these things. So I'd take these things apart and take them home. There would always be a power transformer, and I'd use an ohm meter to figure out what the windings were. And much to my surprise, as I was doing this sometimes, I'd hook the ohm meter up to one of the windings on the transformer, and as soon as I'd disconnect the ohm meter, I'd get a nasty little shock. And that nasty little shock, which I didn't know at the time, was that field collapsing. I was charging up that field, and when I disconnected it, it zapped me. I think you've got a story too, Gary, don't you?
Yeah.
Yeah, when I was working in Liberia at the VOA Liberia transmitting station, we had a modulation transformer go out on one of our GE 250,000 watt transmitters. And we had a bunch of spare transmitters in the basement. And so we went down, but my assistant, he said, some of these are good and some of these are bad, and I'm not sure how we're going to know. Well, I had my trusty Radio Shack ohm meter, analog ohm meter, and as I started measuring windings, one of them nearly knocked me on the ground because of charging it up with DC and then releasing it, the voltage that came back from the thing was higher in magnitude than what I had applied. I said, that's the one you want, that's the good one. And so that's what we used, and we were back on the air.
Yep, very good. So I just thought you might want to be aware of that if you're ever ohming out transformer windings. There's so that field collapses immediately when you take the voltage away. Capacitor will not. It will hold that voltage for a very long time, depending upon if the internal losses of the capacitor. And I don't suppose any of you have ever done this, but back when I was in high school electronics class, one of the little gags that the kids like to do is they'd take an electrolytic capacitor and charge it up to 100 volts, and they'd wrap the wires around the body of the capacitor. Of course, this thing is charged, and then they'd toss it across the room for somebody to catch. So when they caught it, they got a surprise.
I never did that.
Oh no, I'm sure you didn't. Yep. I don't think I did, but some kids thought it was pretty funny. More high school stories, but we'll skip those for now. But those are principles that kind of show you what's happening with storage of capacitors and inductors. Now we'll get into time constants. Time constants look really scary. There's I think it's 5 pages of math in our license manual that talk about time constants. And the good news is you don't need any of that for the pool questions. So if you wanted to work through that, that's fine, but not necessary. They're really scary looking. So what is time constant? So in the case of an RC circuit, a resistor and capacitor, we're going to consider the series case again. The time it takes to charge or discharge a capacitor depends on the values of the resistor and capacitor. So the time constant measured in seconds will be the product of the resistance and the capacitance. And there's a this formula appears on your extra class reference sheet. You just want to note it there. Now with the resistor and coil, it's the same thing. Time it takes the current to increase or decrease through an inductor depends on the values. And then I've got a picture of that here. It's in our book as well. And this is the one and only pool question that you need to know. It takes one time constant to charge to 63.2% or discharge to 36.8%. So here's a little picture up here. So we've got a battery in a switch. The switch is in the charged position. So let's say it's a 10-volt battery. You know, it's going to be in the charge position as soon as we go from, let's consider a discharged capacitor. This has been discharged for a while. We're going to flip the switch up to charge, and then the capacitor is going to start charging toward 10 volts through this resistor. Because it can't charge instantaneously because of the resistor being there, it's going to take a certain amount of time for that capacitor to charge up. So when that capacitor gets to 63.2% of the value of that battery, 6.32 volts, that is what's defined as one time constant. So hold that thought for a second. So seeing it on the chart here, when we flip the switch to charge, it's going to, the voltage across the capacitor is going to start increasing, increasing, increasing. And after about 5 time constants, it's going to be at the 100% level. Theoretically, it would take forever, but in practical terms, 5 time constants is considered fully charged. So that's the charging. So for any place along this curve, you can calculate what voltage you're going to have at what time. And that's what those 5 pages of math are for, which we won't need, because this is the only question you have to answer. Now, what happens when you flip the switch from charge to discharge? Okay, well, at that point, the capacitor has finally made it up to 10 volts, and it's going to start its way back down again. When it gets to 36.8%, these two will add up to 100, by the way. When it gets down to 36.8%, that's also defined as one time constant of discharge. T, or tau, I think that is. Okay. So if you have trouble remembering these numbers, you don't have to remember the exact numbers, just think approximately 2/3, approximately 1/3. So that's the definition of a time constant. For those 5 pages of math, that's basically all you need to know. Now there's one calculation question, a fairly easy one. Okay, what is the time constant of a circuit having 2 220 microfarad capacitors, 2 1 megohm resistors, all in parallel? Well, anytime I see a problem that's like this, and we have problems in other contexts throughout the evening, drawing a picture is extremely helpful to me. So what I've done here is I drew it. We got a 220 microfarad in parallel with a 220 microfarad in parallel with a pair of 1 meg ohm resistors. Now you may remember from your general studies that capacitors in parallel will add. So we're going to draw an equivalent circuit here. So we've got 220 plus 220 is 440 microfarads in parallel with a value of resistance. Resistors in parallel divide. So we're going to wind up with 2 1 meg ohm resistors will be the equivalent of 1/2 meg ohm resistor. So now we've got the circuit in a form where we can apply the formula. So we've simplified the circuit. Here's the formula. Now we've got microfarads and meg ohms. One is times 10 to the 6th, the other is times 10 to the -6th. So we can basically ignore those and just multiply the values. If you want to do it the long way, be 440 E6 times, this is how we'd enter it on our calculator, times 0.5 E6 would come out to 220. That's 220 seconds. There is a little trick here in the question. When you see this one in the pool, it turns out that the answer happens to be right here. It's just a happy coincidence. So when you see this particular question, you can just say, oh, it's 220. So that'll save you some time. But this is how you'd calculate it if you cared to. Okay, let's see what we remember. What is the term for the time required for the capacitor in an RC circuit to be charged to 63.2% of the applied voltage or to discharge to 36.8% of its initial voltage?
Bravo.
It is a bravo,
Bravo.
one time constant. And here's the one that we just did.
Delta.
Delta.
Yeah, 220. And you can see it here, 220, 220. You don't even have to think about that one. But you know how it's done now, so we didn't fail you. So moving on to phase angle. Now we see sine waves all over the place in nature. If you throw a rock in a pond, the waves that extend out from where the rock hit, those are sine waves. A vibrating guitar string, like Kessler showed us, that's a sine wave. And mathematically, let's look at a way to do it. Here we've got a circle. We've got, I guess you could call this a phasor, and we're going to rotate that circle, rotate this phasor around the circle. That should kind of remind you of something. That's how electricity is generated. There's typically a stator and a rotor and the rotating shaft, and as the shaft turns, electricity is generated. So in this case, we got point A, that's 0. This is going to be the 0 point on our circle. We've sort of turned it on its side. At C, when we get around to C, that's going to be its maximum value of voltage. So we're drawing out A through C. We keep going around the circle. We get to, over here to E. We're back at what's called the 0 crossing point. Follow that around, and eventually we'll complete it. So you can see that we can measure time on a sine wave according to the number of degrees that have occurred in the circle. So here's 90, 180, 270, 360, and then it starts over again. So if it took 1 second for this to happen, then we've got a 1 cycle per second, or 1 hertz sine wave. And you can kind of see how phase angle can be equated to time, because 90 degrees, that happens to be this time right here, which in our example would be a quarter of a second. So here's a little picture of why do we have AC voltage? Why is it all sine waves? Well, here's a super simple generator, picture of an AC generator. As we turn the crank, the rotating coil goes past the north and south pole. Then we've got slip rings here, and we wind up with an AC voltage as we turn the crank. So that's why we see sine waves every place. A little bit more. So we demonstrated that phase angle could refer to time, so the number of degrees that have elapsed in the circle would reference a certain amount of time that has elapsed on the sine wave. Full cycle is 360 degrees. And phase angle is measured between similar points on each waveform. Here's two waveforms. It's a voltage and a current waveform in this case. And across, let's say, a resistor. So with a resistor, as the voltage increases, the current is going to increase. So these things track together. So it can be said that voltage and current are in phase for AC across a resistor. And we're going to see that weird things start to happen when we put AC, alternating current, across an inductor or a capacitor. Remember we said that capacitors and inductors store and release energy. It's going to become a little bit more important now. Unlike in resistors, the current and waveforms, voltage and current waveforms they do not rise and fall together. And I'll have a picture of why that happens. And then Eli the Iceman is on our reference sheet as one of the aids. And they describe the behavior of voltage and current relationships in an inductor and a capacitor. So Eli, E-L-I, the middle letter is L. That stands for inductance. So for Eli, inductor, voltage, which is E, and current are shown, which is I. So E comes before I in Eli. So for an inductor, the voltage is going to lead the current. So you can start to get an idea of why Eli is so important. Ice is just the opposite. For a capacitor, current leads the voltage. And I'll have a better diagram of that in just a second. But just introducing the concept here. And the pool questions will ask the reverse sometimes. So they'll say for an inductor, they might say that the voltage is leading the current, but they could also say that the current is lagging the voltage. Now, I don't know about you, but I'm probably not as smart as you are. I can't remember this all in my head. So if I'm dealing with an inductor, I'll actually write down ELI. Then I'll never get which one is leading and which one is lagging confused. So here it is in more detail. The and man have no meaning. It's just to help you remember the memory aid. So L is the symbol for inductance, measured in henries. E is voltage. I is current. So for an inductor, voltage leads the current. E comes before I, except after C. No, that's something else. So E leads, voltage leads the current. Or, said in the reverse, which is equally true, current lags the voltage. So be sure that you know how it works both ways. Ice, C is the symbol for capacitance, measured in farads. We've got current and voltage. Notice that these are swapped around from Eli. We've got E, then I. Here we've got I, then E. So for capacitor, current leads the voltage. Current leads the voltage because it comes first in the word. Or voltage lags the current. So here's another view, giving this to you a couple different ways. Hopefully one of them will connect with you. Now let's look at something that happens with voltage and current. We said voltage is leading, current is lagging, whatever. Well, why does this happen? Okay, so let's look at capacitors to start off with. That's the ice case. So when we first apply a voltage to a capacitor, it takes a while for that capacitor to come up to voltage. So I like physical examples. This is like filling a tank with air. So if you've got a compressor and you want to fill up a tire, for example, when you first connect your compressor to the tire is going to start out flat with no pressure in it. And little by little, it's going to come up to full pressure. But that's going to take some time. So we're going to, in this case, electronically, drawing the parallel, we're going to apply the voltage immediately. But the airflow is going to start flowing. It'll become less and less until that tank is full. So in this case, we can see that voltage, or current, is lagging the voltage. Here it's shown a different way. Ice, the relationship between the AC current through a capacitor and the voltage across the capacitor is that the current leads the voltage by 90 degrees. That 90 degrees is kind of magic. Now here we've got some waveforms. Here's the voltage waveform. You notice at the zero crossing point at 180. It lands here. The current at the zero crossing point happens at 90. So we see that the phase angle is 90 degrees. So the current is lagging the voltage by 90 degrees. Actually, I said that backwards. The current leads the voltage. That's up here. Current is leading. The voltage follows later. It would help if I wasn't misleading you so often. So here we've got phase angle of minus 90. Remember, we were seeing capacitive reactance was negative, and this is how it shows up on a graph. Now, what do you suppose a coil does? Well, it's going to be just exactly, and inductive reactance is going to be just exactly opposite. Here's a little bit more on the capacitor. This is the resistor case. The voltage and current are in phase. With a capacitor, the voltage and current are out of phase by 90 degrees. And it's stored and released twice per cycle. So here's a sine wave coming up, back to zero, down, then back up again. In inductors, okay, here we've got the case of the resistor again. Voltage and current are in phase. With an inductor, here a physical example is a flywheel on a car. So in a car, you've got your spark plugs providing energy to the crankshaft to drive the car forward. But in a four-cylinder engine, each spark plug has to fire before the next one does, and it does that going around the circle. But you may have noticed that your car doesn't jerk every time one of the spark plugs fires. And the reason for that is imparting that energy into something called a flywheel. It's a great big heavy piece of steel. It's inside your engine, like a great big round heavy wheel, and the heaviness of that wheel smooths out those impulses from the individual spark plugs firing. So an inductor works a little bit like that too. It is going to be building up its magnetic field, and then in between the spark plugs firing, to keep that analogy going, it's going to try to give back some of that energy to hold up that magnetic field. So for a resistor, we've seen before, they're in phase. With an inductor, they are not in phase. We only talked briefly about this concept when Gary got zapped by his transformer and I got zapped by my transformer. That effect is called back EMF. EMF stands for electromotive force, or induced voltage. There's some more facts about it. So here we've got the relationship specified. The relationship between the AC current through an inductor and the voltage across an inductor is that the voltage leads the current by 90 degrees. The leading and lagging is important. The 90 degrees is important. And we're talking about a pure inductor. Now, what do you suppose happens when you put a resistor in series with a capacitor? Well, when that happens, the phase angle is not going to be 90 degrees. It's going to be somewhere between 0 and 90 degrees. Just trying to tie some of these concepts together. So for an inductor, Eli, the voltage is going to be leading the current. And for a pure inductor, that's going to be by 90 degrees. Okay, ready for some questions. What is the relationship between the AC current through a capacitor and the voltage across the capacitor? And I'm going to tell you something here that's going to amaze you. This is not going to be written on your test, okay? But from what we've talked about here, you happen to know that this is the ice relationship capacitor. So knowing that, look at this diagram, and if you can't remember it, write it down before trying to answer the question, because there's a real good chance you're going to get it backwards. That's why I normally will write it down, even though I know this stuff pretty well, so I don't mess it up. Okay, so let's try for an answer. Delta. Current leads voltage by 90 degrees. Current leads voltage. In the case of a pure reactance, capacitor all by itself, that will be 90 degrees. Okay, what about the case for an inductor?
Alpha.
A.
Alpha, again, right, it's an inductor, so L, it's going to be Eli, and then you can be sure that you've got this. Remember I said 90 degrees was important? Well, they tried to fool us here with some other things. In current and voltage and current and phase, that would be a resistor. Okay, good, yeah, you're catching it. All right, let's make it more complicated now, complex impedance. Actually, let's see, it's 7:30, so this would be an absolutely ideal time for a break. Last time I did this session, I ran almost an hour and a half before I gave people a break, and they cut my salary. So I want to make sure that we give you a break at about halfway through. So 5 minutes, and we'll be back then. So get up, wander around, get a drink, pet your dog, do something. See you in 5. So good to see you all again. We're going to jump into our next topic right away, called complex impedance. Now we've seen pure resistance, pure reactance, and we're going to look at what happens when we combine these elements now with resistors and with each other. That will be the focus of a good part of the second half here of this evening. All right, so impedance is composed of two components, resistance and reactance. Remember, we had two kinds of reactants, capacitive and inductance. And resistance and reactance can be series or parallel. All of the cases we'll be discussing will be series because it keeps things simple, but obviously they can be connected either way. So we saw that the phasor relationship between voltage and current for a pure inductor or a pure capacitor was going to be 90 degrees. When we add resistance into the circuit, the series circuit in this case, it's going to be somewhere between 0 and 90 degrees. So it depends upon the proportion. Now the sign of the angle depends on the type of reactive element. We saw this before. Negative for capacitance, positive for inductance. So why 90? Well, we saw that a phase shift of 90 degrees is what you get with a perfect inductor or a pure inductor, either capacitive or inductive. No blue text here. Again, this is just kind of background to make the rest of this make more sense. So when we're looking at a problem, we saw this approach with the time constant. If we have a circuit, we can usually simplify it down. If we've got multiple resistors, we just want it to be one resistor. Capacitors and inductors, we're going to simplify that to just usually one or the other. The thing that's neat about inductors and capacitors is capacitive and inductive reactance tend to cancel each other, so you have to figure out which one is dominant, which one is bigger, and then take away that amount of reactance based on the one that's not dominant. That'll make more sense when I show an example. We saw the phase angles. So combining capacitors and inductors will result in a smaller total reactance because they tend to cancel each other to one extent or the other, depending upon which one is bigger. Now, if this was the case, we won't see any of these tonight, but if the capacitors and inductors have equivalent reactive values, they'll cancel each other. The phase angle will become 0, and we're just left with just a resistor. This is just more of a theory thing to reinforce what we talked about. We won't actually see that happen. So let's see what happens here if we want to try to calculate the impedance of an inductor. So we've got a 10 kilohertz signal, 1K resistor, and a 20 millihenry inductor. And we want to calculate the inductive, or we want to calculate the impedance. So I'm going to go over to the calculator cam. Get rid of this because we're done with it. Okay. So what is the formula here? We want to calculate, we know what the resistor is. That's 1,000 ohms. No calculation needed there, but we're going to need to calculate the inductive reactance of the 20 millihenry coil. So I'm going to turn on the coil. How about if I turn on the calculator instead? Calculator is turned on. You always start with a clear key. And here's our formula. XL, inductive reactance, is 2 pi frequency L, which is the same as 2 times pi times frequency times L. L will be in henries. So on our calculator, the way that we're going to do that, well, 2 pi is easy. Here's 2, and here's pi. And then we've got 20 millihenries. Why do I have this saying Oh, frequency, that's,
Frequency.
okay, yeah, I'm confusing myself here. Hopefully I'm not confusing you as much as I'm confusing me. 2 pi times the frequency, that's 10 kilohertz. And kilo is times 10 to the third. So 2 pi, the frequency is 10 kilohertz, 10 EE, 10 to the third power. Now we need to multiply that times the inductance. So here's the multiply key. The inductance is 20 millihenries. That's 20 times 10 to the minus third. 20 EE. And be very careful to use the negation key, not the minus key. Negation 3. Now I'm going to press enter and something useless is going to happen, I hope. It says 400 pi. Well, that's not very helpful. But we have our answer toggle key, which can help us. So I'm going to press that. And now we've got 1.26E3. And if you move the decimal 0.3 places, it'd be about 1260. But if we press the answer toggle again, here we now can see our 1256. It shows all of the decimal points the calculator is capable of. 1256. So X sub L is 1256 ohms. Great, so I'm going to turn this off. So we've calculated the impedance of the inductor. Okay, this is not a pool question. It's a good demo of where we're going though.
We calculated the reactance of the inductor.
The reactance of the inductor, correct. We already know what the resistance of the resistor is because that was given to us. So we're going to keep going now. Now we want to calculate the combined impedance and phase angle. And you're going to be amazed because I think you're going to understand how we do this. So R is 1,000. We just calculated the inductive reactance of the coil. And now we're going to write this in a rectangular form. See how this is coming together? It's going to be 1,000, value of the resistor, plus, because it's inductance, plus J1256. And then we want to convert this to polar form so that we can see the phase angle. All right, so let's go ahead and do that. Go back to the calculator. Turn it on. So we want 1,000. Clear it? Yeah, okay. 1,000 plus, I'm going to put it in rectangular form, plus 20 millihenries. All right? And we calculated the inductive reactance as being 1256 just now. Plus, but it has to go in, the impedance has to go in as a complex number. So it's going to be I. Triple tap the pi key. 1, 2, 3. 1,000 plus I. 1256. And if we're really lucky, we're going to wind up with the phase angle of that impedance, which is about 51 degrees. 51.5. Second off. Coming back to our slide again. So the phase angle is 51.5 degrees. Now we want to know if voltage is leading the current or the current is leading the voltage. So it's an inductor. So it's Eli. So voltage is leading current. So we now know the combined impedance and phase angle of this circuit. So I hope you see how the concepts are all starting to fit together. And with that, we can jump right into a calculation question. All right, and here's the question. And I think I've got a diagram. I do. Okay, let me back up. Well, I just gave you the answer, but what is the phase angle between the voltage? What is the phase angle between the voltage across and the current through a series RLC circuit if X sub C is 500, R is 1 kilo, and XL is 250 ohms. Okay, so I'll just kind of give you a little preview here. We have to find out which reactance is dominant. So notice that XC is 500 and XL is 250. So because these cancel, we're going to take the dominant one, which is capacitance, and reduce it by 250 ohms.
It has to be a lagging question, right?
Well, let's see. Let's go back. We decided that capacitance was dominant, right? So that's going to be ice. So when you say lagging, it could be voltage lagging or current lagging. So be careful. You have to be real careful how they're asking the question or how they're giving the answer in this case. They've got a combination of leading and lagging. So hold on to that thought for a minute and let's look at the diagram. So here it is. What are they asking for? They're asking for the phase angle and what the lead-lag relationship is. So what I'd recommend is drawing it and showing the values. Here they are. Second, determine which one is dominant. Well, it was the capacitor because that's 500 ohms. Inductor is 250. So reduce the larger by the smaller. Result is going to be 250 ohms capacitive, because that was the dominant one. Enter it in rectangular form. 1000 minus I250. 1000 is the resistor. We know the combination of these two gives us the I250. I'm going to press enter. Should come up with a phase angle of 14 degrees. And then because we're using capacitor, we're using ice, so voltage is lagging the current. But let's flip back to the pool question. So we know it's going to be 14 degrees, which we calculated. Now, this is the trick here. They give us both leading and lagging. So it's ice. So which one would it be, B or C? And again, what I would do is write down ice, and then that will answer the question, which one it is.
Charlie.
It is Charlie, yes. Then I'll come back to the calculator cam, just to reinforce what we just did. Turn on the calculator. Okay, and that was 1000 minus I250, 1000 minus I, triple tap the pi, 250, enter. Okay, here's our 14 degrees. Now it's showing negative 14. We know that the phase angle is going to be negative because it's capacitive. And here's ice, so we can tell if either we're going to have current leading or voltage lagging, and then we have to pick out the right answer in the pool question to see which way they're querying us on that. So very good. Hopefully you followed us through all of that. So for each of the next couple here, I've taken exactly the same approach. We won't actually calculate each one on the calculator because they're all done the same, but I'll point out the differences as we go. Now in past presentations, if any of you looked at one of our past presentations, there was a little trick. There's 3 questions like this, and every one of them was 14 degrees, okay? Well, the people that do the pool questions, they changed the values so that they're not all 14 degrees anymore.
Darn it.
Oh, darn it, yeah. So if you saw one of our past extra presentations, that shortcut will not apply. Okay, so you actually have to figure these out. Okay, we saw that one. Okay, here's another one, all right? And we'll just kind of, we'll walk through this process. We won't actually calculate it all the way through, but we'll talk through it. Phase angle between and the voltage across and the current through series RLC circuit if X sub C for some reason they didn't use X sub C, they just say XC, doesn't matter, is 300 ohms, R is 100 ohms, and XL is 100 ohms. Okay, so again, let's see which one is dominant. XC is bigger, right? So we're going to reduce that by this value and then plug it in. It'll come out to 63 degrees with the voltage lagging. So I've gone through the same steps here. I've diagrammed it, which I recommend that you do as well. It's asking for phase angle, lead lag, draw and show values. We decided that the capacitance was dominant. It's bigger. Reduce the larger by the smaller. So 300 minus this, so we're going to wind up with a resultant capacitive reactance of 200 ohms. Negative, because it's capacitive. Very much like the previous problem, except it's different values. Enter in rectangular form, enter it into the calculator. Press enter. And this time the phase angle comes out to 63 degrees. And using ICE, we can see that voltage is lagging the current. We go back to the question. That's how they ask it. Now sometimes they say leading, sometimes they say lagging. That's why I recommend you write down ICE or Eli so that you don't get these backwards. It's super, super easy to get them backwards. Okay, that's the second one. Here's the third one. Let's see if there's anything different about this. Okay, now this time inductive reactance is dominant. It's 75 ohms. Capacitive reactance is smaller than inductive reactance, so that this one's going to be just slightly different. The answer is going to be that. Okay, I've diagrammed it, showed the values. In this case, the inductor is dominant. That's 75. It's the bigger of these two. It's going to leave us with plus 50 ohms of inductive reactance, positive because it's inductive. We'll enter that in rectangular form on the calculator. Press enter. Come up with a phase angle of 27 degrees. And because of Eli, L for inductor, the voltage is leading the current. And there's the answer. So hopefully having kind of, we did one completely and then we just talked through the other two. These are the only three that could possibly appear on your exam. And because these are all within the same group in the question pool, you'd only get a maximum of one of these. But for those of you that wanted to get 100% on your test, you will need to be able to figure out each of the three, so you won't get that one wrong, if you get it. All right, now we're going to raise the stakes just a little bit. In these past cases, they actually gave us the inductive and capacitive reactance. Well, that was really nice of them, because remember, these are frequency dependent. We don't know what the frequency is. They didn't tell us. We just know that whatever this frequency is, this is the inductive and capacitive reactance. All right, so that was very nice. Now we're going to increase the complexity by, they're going to give us a frequency and a value of inductance or capacitance. And we have to figure out what the reactance is using either inductive reactance is 2 pi frequency L, or capacitive is 1 over 2 pi frequency C. You're going to memorize those two. You might not believe me right now, but you will. Okay, so now onto this. There's, I think, 3 questions that are set up the same way. You might not be able to read this very well, but I'm going to recommend that you turn to page 4-21 in your book. Then you'll be able to see this a lot better. Okay, I'm going to make another recommendation, because after figuring out how to work this, how to calculate it, I'm going to give you a shortcut that's going to make these extremely easy. And for that shortcut to work, I need you to make an assumption with me. See this 0.8, and I think this is 0.6? They're very, very close to the x-axis. This one looks like it's actually right on the x-axis. What I'm going to recommend to you is that you consider both of these points as being right on the x-axis, okay? If you'll do that, there is a shortcut that will make all of these questions very, very easy to answer without doing the calculation. But let's do the calculation first and kind of see what happens. Now, hopefully I've got that. Well, we're going to wind up giving you the answer first. It's going to be 0.4, but we're going to work through it now. So it's asking which point on the diagram. We need to know the resistance, and we're going to need to know the capacitive reactance. Now, where are we going to need to know those two things? Well, because that's what it's giving us in the question. What is the impedance of a series circuit consisting of a 400 ohm resistor and a 38 picofarad capacitor at 14 megahertz? So the value of the capacitance and the frequency we have to deal with now. So here I've diagrammed it. Resistance 400. We've got the capacitance 38 picofarads. We've got the frequency. And when we work this out, the capacitive reactance should wind up to be 299. Let's see if that happens. So draw it. We need to calculate x sub c. And here's the formula. X sub c equals 1 over 2 pi frequency c. Let me see if I've got a... Yeah, I do. Okay. Let's go over to the calculator cam. I didn't remember if I had a card for this one or not. Turn on the calculator. So what we're shooting for is to come up with an answer for what is the capacitive reactance. When we get that, we can put all of these values in polar form into the calculator to get the rest of the information we need. Okay, so the formula is x sub c equals 1 over 2 pi frequency c. So to do that, we'll want to use the fraction key, make it clear. This is the fraction key, box over box. And we're going to put 1 in the numerator, it's the upper box, 1. And then get to the lower box, we use the navigation diamond. Now the bottom box is blinking. Now we want to put in 2 pi frequency c, 2 pi fc. 2 pi, the frequency is 14 megahertz. That's 14 times 10 to the 6th. So 14 EE, key gives you 1 E in the display, 6. 14 times 10 to the 6th is what that means. And then we need to multiply it times the capacitance. So we'll use the multiply key, get an asterisk, which is its symbol. And then we need to put in 38 picofarads. Remember, picofarads is times 10 to the minus 12th. So that's 14.
No. 38.
Thank you. 38. I used the delete key to back up. You could have cleared the calculator and started over. Thank you for watching me, Gary. 38 EE. Then the negation key, that's this one, not this one. The negation key, 38 times 10 to the minus 12. Enter. Oops, I didn't hit it. There we go. That gave us 299.16. So X sub C is 299 ohms. All right, so let's pop back over to the to our question. So we now have everything that we need to know to plot this point. We know that the resistance is 400 ohms, so we're going to move over to the 400 ohm point. And hopefully you're looking at your page 4-21 because this is really hard to see. And then it's capacitive reactance, so it's going to be negative, right? So we're going to come down 300. Okay, so that sure looks like it would be 0.4. So let's see if 0.4 is the answer. Okay, now are you ready for the shortcut? So you don't have to calculate all of this. I wanted you to see how to calculate it, and please try the other ones as well. But let's see what we can figure out. Remember I said we're going to assume that these 2 points are on the line, so it's not going to be one of those. So it's a 400 ohm resistor, so we know we're going to be 400 to the right, and it's going to be some kind of capacitance, which is going to be below the line, and at 400 there is only 1 point that's below the line. So it had to be 0.4 without having to do the calculations. So hopefully you can see how that works. So let's try the shortcut on the next one. So we just went through this one. All right, this one says it's a series circuit, 300 ohm resistor, so we know we're going to come over 300, and an 18 microhenry inductor at 3.505 megahertz in the 80 meter band. All right, so we can go through the process for figuring out inductive reactance, X sub C equals 2 pi frequency L, and come up with the inductive reactance. But without doing that, we can tell from this chart, it's inductive, so it's going to be up. So it can only be 0.3. You see how I did that? So that's a way that you can either double check your work or avoid doing the calculation entirely. Could we be that lucky on the third one? Let's see. All right. So here's the third one. Here we're dealing with a 19 picofarad capacitor in 21.2 megahertz in the 15 meter band. So let's see if that works. 300 ohm resistor, 300, 19 picofarad, so it's going to be down. There's only one value shown on our chart, which is 0.1. So there it is. So that shortcut will work for all three of those problem types.
But Dave, what about points 5 and 7? They're lonely over there.
Yeah, 5 and 7. Remember, does anybody remember what we talked about with points that are to the left of the y-axis? You can't have negative resistance, right? So it can't possibly be these. Yes, good question. This will be a little easier to read in your exam. That's why I referenced you to page 421 in the book to follow along with us. We did it. Okay, now admittance and susceptance. We've just got 2 sections to go here. We're probably going to get out a little early tonight. And the reason for that is they've taken a bunch of questions out of the pool. So I'm sure after all of this heavy lifting that we've done tonight, you could use a few minutes early. So admittance and susceptance. Now, this is something that you will probably never use in your ham radio career, ever. I never have. If you get into engineering, there are some very good uses of admittance and acceptance, and Smith charts happens to be one of them. I don't know if Gary will mention that when we get to that part of the book, but basically what I'm saying is that it's going to be rare, if ever, that you're going to use these. But there's 5 pool questions, good grief, 5 pool questions that they drew out of this material, and they're really confusing. Very confusing. So I scratched my head, it hurts without any hair, and tried to come up with some shortcuts, some memory tricks to help you get all 5 of these questions right. You're still going to have to think. These would be really hard to memorize because they're so interrelated. But let's charge forward and see what happens. So from the extra class reference sheet, in the AIDS section, you've got something that looks like this. Now on your copy, and I just discovered this today, the only pool question that we need this for, I had the values for this one in, so I had X and B instead of Z and Y. So you can either mark up your sheet accordingly, or I'll be updating the sheet as well. Not super important, I just wanted to point out the difference. So memory tricks. Okay, now the pool questions use both the terms reciprocal and inverse. Now remember what we said in an earlier session about reciprocals or inverses, an indirect relationship. Anytime you've got 1 over something, that's an inverse or a reciprocal. So we could say that impedance, to get to admittance, that's the inverse or the reciprocal of impedance. 1 over admittance. So that's, and there's a couple pool questions that come up that way. Just, I want you to be aware here that this means the same thing. One value is 1 over the other value, or vice versa. Okay, now, next, we need to somehow associate impedance and admittance. We need to tie those together. The way that I do that is with a door metaphor. Here's somebody coming through an open door. So when the door is closed, you are impeded from entry. I think I had this in the reference sheet tutorial as well. So when the door is closed, you are impeded from entry. When it's open, you may be admitted. So impedance and admittance are associated in this formula here. Now, we don't have to calculate anything that I'm about to talk about. We just need to know principles about how they work. Now, this one here is the most arcane, confusing, impossible to understand statement that we have to deal with. Converting impedance to admittance. Now remember, impedance and admittance we've associated. In converting to impedance to admittance, in polar form, you take the reciprocal of the magnitude. Remember, polar form, it was magnitude and direction, or magnitude and angle, and reverse the phase angle. Now, it's hard to understand this. It's even harder to remember it. But when you get to a pool question that has this as an answer, that's the right answer, okay? So that's a way that you can remember this one and get it right. If you want to understand the theory of why that is true, our book, Extra Class License Manual, it's pretty tough to figure out there. And Kessler didn't help us any either, but anymore. The trick here is if you see this thing, reciprocal of the magnitude, reverse of the phase angle, if you see that in the question list, pick it, it's right. So those are some memory tricks for impedance and admittance. Now we're going to talk about reactance and susceptance. Got some memory tricks here for you. So we need to associate reactance and susceptance. So some kind of an image or picture to do that for us. So we're going to talk about suspicious Bob, all right? So this is Bob, and he looks kind of suspicious. He's kind of not looking right at us. He just looks like he's up to no good. Bob is suspicious. Susceptance. Notice that Bob's first initial is B. There is a pool question that asks what is the common letter for susceptance. Well, if you can remember suspicious Bob, you've got it. Okay? So Bob is suspicious. And Mary, over here, she's going to react to this scary-looking guy. Look at the look on her face. She doesn't look very happy, does she? Sees this guy and she says, "Ah, what's going to happen to me? Is this an insurance salesman going to try to sell me something I don't want?" So Mary reacts to suspicious Bob. React, reactance. Suspicious Bob's first initial is B. But Bob is harmless because he's imaginary. He's your imaginary friend. So all of these silly words here are memory tricks or crutches or memory hooks to help you with the actual pool questions. So let's see how this works. Okay, first, admittance is the inverse of impedance. Admittance and impedance, you see the inverse relationship, 1 over. And notice the blue text. Now we're putting these in context to the pool questions. Converting impedance to admittance in polar form, take the reciprocal of the magnitude, reciprocal of the value, and change the sign of the angle. Now in polar form, of course, we're talking about angles. So this is another one that's very confusing. So if you see these words in a pool question answer, they're the right words, okay? So that was the admittance case, admittance and impedance. We'll consider the 3 pool questions, and there were 2 pool questions for admittance. There's 3 pool questions for susceptance. It says, what is susceptance? It's the imaginary part of admittance. Okay. Why? You can try to figure it out if you want, but take my word for it. If you see these words in a question set, an answer set, that's the right answer. Okay, the next pool question we're going to see, effect of pure reactance magnitude when converting to susceptance, replaced by its reciprocal. I think there's more words in there than you probably need. You know that reactance and susceptance are associated, and to get from one to the other, you just take the reciprocal. These words make it sound a lot more complicated than it is. And then B is the letter commonly used to represent susceptance. Remember suspicious Bob? Well, B stands for Bob. Okay, so I hope that those are going to help you. Let's see. How is impedance in polar form converted to an equivalent admittance? Remember I said if you see these words, it's the right answer?
Bravo.
Bravo. Take the reciprocal of the magnitude and change the sign of the angle. You might have to go through these a couple times to make all of the associations, but I believe that they'll work. What is the effect on the magnitude of pure reactance when it is converted to susceptance? Now the reason that
Delta.
the reason that I highlighted this, which won't be in your test, magnitude implies polar form, right? Okay, that might be helpful, I don't know. But it is D, it is replaced by its reciprocal. What is susceptance? Remember I said if you see these words, it's the right part. Bob is our imaginary friend, imaginary part of admittance. What is admittance?
Inverse of impedance.
Yes. Remember the door? You admit or you impede, and it's going to be the inverse. One is 1 over the other. What letter is commonly used to represent susceptance?
B.
Delta.
Suspicious Bob, right? And caution here, notice that there's an answer. There's a letter in the answers. It's the same as the right answer. These are going to be probably in a different order if you get one on your exam, but just be really, really careful that you're looking at this and not this. Okay, we've got one more section to go, reactive power and power factor. This was a really big section in the previous poll. It's a very small section now. I think there's 2 or 3 questions, or four pool questions. You can take a sigh of relief right now because we're past the brutal part, and none of that was really that terrible. I think the hardest part was the admittance susceptance stuff. So hopefully I gave you enough clues there to help you through it. Okay, these are just some general facts now. Power equals voltage times current. We learned this back in the technician class. Expanded on it in the general. So you probably remember this from the pi and ear charts that we discussed. Power is voltage times current. That's true in a DC circuit. Now in AC, some weird things start to happen. We have a concept called apparent power, and I'll have this demonstrated on the next slide. Now, the thing about apparent power is it doesn't take into consideration the phase angle of reactive components in the circuit. So that's why this won't work for a circuit that has reactive components in it. So, but you can measure the voltage from a power source and the current that's flowing out of it, and that, rather than being called the watts like it would be in DC, is going to be expressed in VA, volt amps, which would normally be watts in DC, but we're going to call it VA in AC. Now here's an interesting fact. Remember I said that voltage and current are out of phase in an inductive or capacitive component. Therefore, no power is absorbed by that component. Those components absorb and give back power. they don't give back energy. They don't actually consume any power. So reactive power, which is kind of a misnomer in itself, is wattless, non-productive power. And reactive power in an AC circuit that has both ideal inductors and ideal capacitors is repeatedly exchanging energy between the associated magnetic and electric fields, but it is not dissipated as it would be in a resistor. That's why an inductive element or capacitive element will not generate any heat. It won't dissipate any energy, which is why it's wattless, non-productive power. So the relationship between the voltage and current for reactive power, they are 90 degrees out of phase. And of course that would be true of a pure inductance or a pure capacitance. Because they're out of phase, they don't dissipate any power. So here's an example. We've got a circuit here. We've got a voltage source, 200 volts AC. We know that the current flowing is 1 amp. Okay? So what we're going to have here is the VA number, voltage times current, is going to be 200. So you would think, incorrectly, that the circuit would be drawing 200 watts. But because we have an inductive element in here, which is wattless, the only thing that's going to be absorbing any power is the resistor. So because it's a series circuit, we know that the same current flows through everything in the circuit. So by using our Ohm's law figure, power equals I times R, or I squared R, we can see that we're going to wind up with 100 watts of power consumption. It's only the resistor that's going to be absorbing any power. The inductor will not absorb any power because the voltage and current are out of phase through this component. So the apparent power is going to be 200 volt amps, 200 times 1. And the power factor, which we don't have any questions on this, but that's the real power over the apparent power, which is 0.5. We can see that we think, if we just look at this portion here, that we're going to be consuming 200 watts, but we're only going to be consuming 100 watts, half as much. So that's why the power factor is 0.5. So just walking through this, we saw that current and voltage are not in phase through XL, so no real power is consumed. Real power is consumed by the resistor only. Power equals I squared R from our Ohm's law. Days, which is 100 watts. And again, the inductor consumes no power, wattless, non-productive power. So with that very brief introduction of this concept, I think we can answer all the pool questions, and we'll be done. What is the phasor relationship between current and voltage for reactive power?
Really?
They
It is Charlie, 90 degrees out of phase. Now they don't specify if it's an inductor or capacitor, but if it's only reactive power that we're talking about, it's going to be one or the other. It's reactive. There's no resistance in the circuit, which makes it 90. What happens to reactive power in ideal inductors and capacitors?
Baker.
Baker. Yep, energy is stored in magnetic or electric fields, but no power is dissipated. Power is not dissipated. I have to kind of chuckle at some of the the wrong answers are called distractors. I love C. It is canceled by Coulomb forces in the capacitor and inductor. Well, no idea what they're talking about. So how real power is consumed? It's probably supposed to be how much real, but anyway, how much power is consumed in a circuit consisting of a 100 ohm resistor in series with a 100 ohm inductive reactance drawing 1 ampere. Okay, well, it's a series circuit, so it's going to be the same current through every element. We kind of saw this in our example. Power is I squared R. So I is 1, I squared is 1, R is 100. So it's going to be B, bravo, right. So that's a real easy one, and there's a shortcut or a trick here. If you see this one, this 100 and that 100 match, so you don't have to think about it too hard if you can remember that shortcut. What is reactive power?
Delta.
Delta, wattless, non-productive power. And guess what? I think we're done with part 1 of chapter 4. The heaviest lifting we've done tonight in chapter 4. There's a few more pool questions that we'll be covering next week, and a few more topics, but many of them are easier. We've done the tough stuff in chapter 4. So we're into the class chat portion. We are a few minutes early. I'm hoping somebody will comment on if you found that to be helpful, if you think you can actually get through these right now. So it's your turn.
I just wanted to make a comment first about why do we have to talk about admittance and all susceptance, and where does that come in? As Dave mentioned, the book mostly covers series circuits for complex impedance. But there are times when you need to do calculations in parallel circuits. Yeah. And so that's where admittance and susceptance comes in, because it's sometimes easier to work with those values in parallel circuits. Mm-hmm. So that's why they exist. That's why engineers need to know about it. But for our purposes in passing the test, we just need to know the general concepts. And then the other thing about wattless power, it's the bane of power companies.
Oh, yes.
Because power companies have to build their power distribution and their power generation systems for reactive power, for the non-productive power. And they hate that, because they have to push all that power out in order to get the real work done. And so that's why they're really heavy into power factor correction in industry. So if you're working in a factory or whatnot and you see a big bank of capacitors at your power input to the plant, that's what they're doing. They're compensating for power factor of inductive loads.
Right. You'll see those in power substations as well. I think Kessler had a picture. Humongous capacitors to counteract that. All right, anything from our class?
The Cartesian plot, the ones that were negative pure resistance, there's nothing that has to do with susceptance or nothing like that. They're just, what do they represent in theory?
We covered what we need for the pool questions. You could convert reactances to susceptances and go through some stuff like that, but it's way heavier than...
It's beyond the scope of this class.
Absolutely, yeah. And the book gets into some of that kind of stuff. So if you're really turned on by this, the 2% of you who might be, go for it. The other 98% of you couldn't let it slide. So do you think you could do these now after we work through them? We're getting any heads
See the thumbs up.
Yeah, okay. Very good.
Thank you, guys.
Yeah, you bet.
Alrighty.
That's all we have. So for next
later.
Yep. The rest of the rest of chapter 4 for next week, and I'll be sending out an email with a couple more handouts.
Thanks, y'all.
Yep.
73.
Thank you, guys.
Yep.
Thank you.
Good night.
Hey, Gary. Hey, Jim. Jim Grigsby. You guys.